Okay, so today we're going to be looking at electrophilic addition of halogens or hydrogen halides upon double bonds, alkenes. In year 11 you would have seen this reaction, but you would have seen it without the mechanism. So for instance, ethene plus bromine without any special reaction conditions, just room temperature, no need for UV light either. You get an addition reaction which forms this compound here, bromine, there you go, 1,2-dibromo ethane. If you were to use hydrogen bromide, for instance, instead, very similarly, same thing applies. You're going to get an addition reaction across the double bond, hydrogen on one side, bromine on the other, you get bromoethane. And that was about it. Now when you get to A-level chemistry, they're going to ask you to show them the mechanism for this reaction, like how does this reaction actually take place? How does it work? Why it doesn't need UV light? Well, let's have a look. Let's start with ethene, for instance. Just going to draw the hydrogen on this side. It's not quite orthodox, but we're allowed to do that. And I'm going to draw the hydrogen bromide here like this. You'll understand why in a minute. So, hydrogen bromide, okay, being a covalent compound, but the bromine is more electronegative than the hydrogen. So, the electron cloud will shift towards the bromine, leaving this one with a slightly more negative charge. We're going to say delta negative, and this one becomes positive. That's a positive charge density, negative charge density. Effectively what we have in chemistry is known as a dipole. This region here on the alkene is quite rich in electrons. So you've got electrons that are above and below the axis between the two nuclei, which are going to be attracted to this positive charge density here. So I'm going to move two of those electrons to attack the hydrogen. Note, I've used a double-headed arrow here because it's the movement of two electrons. And then as those electrons come in, those two electrons come out from the bond onto the bromine, another double-headed arrow. What that leaves us with is going to be, okay, double bond's no longer there. We've used those pi bonding electrons. The hydrogen attaches itself to one side of the double bond, and this carbon now has one electron less than it should do, so that becomes a carbocation, okay, a positive charge on a carbon. What we're left with is a bromide ion, and a lone pair on that bromide ion will attack that carbocation there to give our product. Okay. Note, I didn't use the arrow, I didn't start the arrow from the charge. The charge just tells us what the overall charge is, okay, that negative there. But the attack is with two electrons. Now that's all very well, but what if we had, for instance, bromine, instead of hydrogen bromide, bromine? Alright, let's get rid of this. No, it's going to be very, very similar. Once you can do once you can do the mechanism once, you can do it again and again and again. Let's put the bromine in here. So of course, if you were to be asked which is the most electronegative, bromine or bromine, well that question makes no sense. And what you may remember from physics though is that we can have what are known as induced dipoles. So as this bromine molecule comes close to the electron-rich area here on the alkene, these electrons of the bromine are going to shift away, they're going to be repelled, and what you get is an induced dipole similar to the permanent dipole that you would have on the hydrogen bromide. Once this happens, same applies. Two electrons from here attack the bromine. These two electrons move on to the bromine, and you end up with very similar to before. This time we've added a bromine. We have a carbocation there. Bromide ion here, that forms a bond. Okay, so those two electrons to the carbocation, ending the reaction and giving us the product 1,2-dibromo ethane. Right, that's all very well, but usually in tests what they do is they'll ask you for non-symmetrical alkenes. So for instance propene. Propene is usually a go-to, it's quite a classic. Okay. I'd say it probably appears in about 50% of all tests, at least. So, 1, 2, 3. Draw it displayed for now. You can draw it skeletal, unless they demand that you put it in displayed form. And if it was just bromine, there's no problem here, because bromine goes onto one, bromine goes onto the other. You're always going to end up with the same product, the 1,2-dibromopropane. However, if we had hydrogen bromide or hydrogen chloride, won't make too much of a difference. Okay, everything is the same so far. We've got a positive charge density there, negative charge density there. Those 2 electrons there will attack the hydrogen, leaving a carbocation behind. Those 2 electrons move on to the bromide as it leaves. But now the question is, well, which carbon is that hydrogen going to be attached to? Well, it could be either this one or this one, of course. So now we're going to have potentially 2 products. We could get the hydrogen attaching itself to the first one, leaving the carbocation on the second carbon, or we could get the hydrogen attaching itself to the second carbon, leaving behind the carbocation on the first carbon. The rest is the same. We have the bromide here, patiently waiting for the carbocation. 2 electrons move into that position there. That's a double-headed arrow. Into there like that. And we end up with 2 different products. Hydrogen, 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 and then the hydrogen there. So bromine on the second carbon there, that would be 2-bromopropane. Or in this case we end up with bromine on the first carbon to give us 1-bromopropane. Now, in the test they're always going to ask you, okay, well, which is the major product, or show me the mechanism that produces the major product. Well, heads up, this route here is going to be the major one, and this one will be minor. It's approximately, if you want to give it some numbers, 70%, 30%. These numbers you do not have to learn off by heart, you just need to know which is the major, which is the minor product, okay, or the major route to get to the major product. But why does this happen? Okay, so this is another question that we like to ask, well, why? So the difference between these 2 is the type of carbocation that we're going to be leaving behind in the intermediate. Now, it's not easy to form a carbocation, okay? You're removing an electron from a carbon, leaving a positive charge behind. This is not something easy to do. It's not favourable energetically speaking. So anything that can make that easier will make it more likely to form that carbocation. So in this case here, this carbon has 1 carbon next to it, and that carbon has electrons surrounding it, and those electrons can shift towards where this positive is going to be formed to cushion the charge that's forming. Okay, so it doesn't become a full charge if you've got electrons here that are shifting towards it to dampen that effect, that positive charge. In this case up here, we have 1 carbon and another carbon, so 2 carbons that can loan some of their charge density, okay, to cover the formation of that carbocation. If there's 1 carbon, okay, it can happen, but if there's 2, it's more likely to happen. In a nutshell, that means, if you remember your energy level diagrams, where you've got energy over here and the reaction coordinate down here, we have the reactant here, this one, the products down here. Now, to get from there to there, we have to overcome an energy barrier, which is forming the primary carbocation. But because of the two carbons that are adjacent to that cation there, the activation energy through that route is slightly less. I'm not saying it's easy, I'm just saying it's easier. So, less energy required to go through a secondary carbocation, and therefore, once that's formed, the bromide attaches itself and you end up with the product. The major product being the 2-bromo-propane. Okay. And like I said before, these numbers you do not have to remember them off by heart. If there was a chance of forming a primary versus tertiary carbocation, then it's approximately 10 to 90, the difference. And if you have secondary versus tertiary, it tends to be, again, 30-70, something like this. So like I say, in the exam, they won't ask you for both, they'll ask you for one, usually the major one. So you draw this one. As a standalone question for 1 mark, they might say, okay, well, which is the other product, the minor product? Draw 1-bromo-propane, and you bag yourself 4 marks. Slight nuance now. What if they asked you, what happens if this reaction was to take place with bromine, but in an aqueous medium? So we talk about bromine water. Now, back in GCSE, you would have done the reaction of bromine water. It's a test used for alkenes. It goes from orange to colourless. We're breaking the bromine to bromine bond. But what are the products? Right. Well, let's go for propene. Oops, apologies. Let's go for propene again. What happens if we were to add bromine in aqueous medium? Well, if it was just bromine on its own, okay, bromine goes in there, then bromine goes in here. Or bromine goes in here, then bromine goes in here. You get the same product. But if you use aqueous bromine, okay, so bromine water, what you get is the following. There's my bromine, positive and negative charge densities there, induced dipole. Those electrons attack this one here, kick this one out, and we're going to end up with, well, I'm just repeating myself. So we said the hydrogen, in this case, sorry, the bromine attached to this one, you made a mistake there, and the carbocation being formed there, or here we have 2, 3, 4. The bromine attaching itself to the second carbon, leaving a carbocation there. Everything the same so far, except we've started with a bromine instead of a hydrogen. Yes, we have bromide ions, but have been formed, so I'll just put the bromide ion down here just to remind ourselves. In water, okay, in aqueous solution, this bromide is competing with water molecules. Okay? And there's many, many, many more water molecules there are than bromide ions being formed. So, yes, bromide can go in, you can get the 1,2-dibromo-propane, but what typically happens is this. Okay, the same will happen down here. You have pairs of electrons here that can attack that carbocation as it's being formed. So the 2 electrons attack that bromide. As this one is leaving, the water molecule is already attaching itself. In this case, for instance, you will end up with 1, 2, 3. Here's the bromine. Okay, so water goes in. Now this is the part that you don't really have to detail too much. Okay, normally what we just do is write OH here. Okay, I'm just going to put the H there like that. And we've lost a hydrogen ion from the water, a bromide ion from here, so there is a byproduct, and the byproduct is hydrogen bromide. So that would be the major product. This one here, we'd have the water attacking that carbocation there. Okay, so we've got water there, bromine here, hydrogen, hydrogen. Okay, so then the products are, like I say, slightly different. This one here would be 1-bromo propan 2-ol, and here we have 2-bromo propan 1-ol with the hydrogen bromide byproduct. We still consider them addition reactions, but obviously in this case we have a byproduct of hydrogen bromide. So if they're asking you to draw the products of the reaction of, say, propene or any alkene with bromine water, then what you're going to need to do is 1 bromine and a hydroxide here, or the other way around. That will be the major one, minor one, and there's even chance of a third product, which would be 1, 2, 3 bromine here and bromine there, but very, very, very minor. Okay, so technically there's 3 products: major product, minor product, very, very, very minor product. Now, for those of you who want to delve a little bit deeper into how does this become this, let me just make a little bit of space here. Okay. Okay, so I'm not going to draw the whole thing out again. We've got the double bond attacking the bromine. These 2 electrons here move on to that bromine there, leaving behind a bromide. But it's competing for that position with the water molecules. There's a vast amount more of water molecules. So that electron pair attacks that positive charge there. And what we get is, like I said, this is not really something that they're going to ask you for. Well, they shouldn't anyway. They might do, who knows. Bromine there. O. We've still got the 2 hydrogens on. There, just made the bond a little bit longer to fit it in there. So 2 electrons have moved to here to form a bond. That carbon has received an electron, there's the electron, and it got it from the oxygen. So as you know, that species has a positive charge, that one has no charge, so +1 on 0 is still going to be plus. So this thing is positively charged. Where's the positive charge located? Well, it's located on the oxygen, okay? That oxygen should not have 3 bonds. But that's got an easy solution. What happens now is, that technically you've seen that in chemistry as a dative bond. So 2 electrons from here move on to the oxygen, okay, releasing a hydrogen ion. Let's draw it down here. Bromine, giving the OH that I showed before. Draw the bond from the carbon to the oxygen, not to the hydrogen. They will pick up on that. 1 hydrogen has left as a hydrogen ion, and don't forget the bromide ion over here. Bromine negative, remove that, and there's our byproduct. Hydrogen bromide as a byproduct, and our 1-bromo propan 2-ol.